Folks, are you able to see my screen? Am I audible to everybody?
Yes, sir, you are audible.
Okay. Shall we get started?
Yes, sir, we
Kalpesh?
can. Yes, sir,
Okay,
we
great.
can.
Great. All right. Good morning, everyone. Sorry, there was a little bit of a technical glitch sharing the screen, but now that's sorted. So good morning to everyone, and sorry for the delay. Um, I wanted to give a quick introduction of myself before we get started. I'm Karthik. I work as a chief architect at IBM. I manage a portfolio of mobile security products and have been with the organization for about 20 odd years. Today's topic is something that is very close to my heart, and I have been over the last maybe couple of decades uh, building products that have essentially had problems to deal with around performance, scale, reliability, and through the course of these 2 decades, I have considerable experience in trying to manage and build out on some of these products. What I will be sharing today is a session on performance, scale, and reliability for software products. And we will try and make it a little bit of an interactive thing, collaborative thing. I would uh, like to keep it very interactive in the sense that when there are questions, I would like to see some answers. I would like to see questions clarifying certain points that I make. So feel free to pause me in between or raise your hand, and we can definitely take questions at any given point of time in the session. Right. So with that, and no further ado, let me kickstart the session. Okay. So many of you would have taken the previous course around software design and architecture that I had conducted. I think we spoke at length about what design and architecture mean in the world of software. We drew parallels between the world of civil architecture and many examples that the whole concepts of software architecture are derived from. And we had spoken about requirements and how some of the requirements for software actually contribute to both design and architecture, right? So, really speaking, what design and architecture in software are is essentially activities that you are involved in when you are trying to conceptualize, frame, commission, decommission sometimes, modifying software systems, etc., depending on the need of the software, right? And when we talk about the need for software, you have certain product management people, etc., who are giving you requirements, and some of these requirements come directly from the consumer, right? So usually those consumer considerations in requirement specifications are called functional requirements. And then there is the producer who's producing the software. That person has a lot of considerations when he or she is building software as well. Those requirements are called non-functional. So it's not directly something that the consumer sees, but they are equally important Yes, Berlin. Yeah, you had a question. Okay, never mind. Yeah, so the producer's considerations are equally important and usually are termed as non-functional. Now, if we were to maybe draw this out and try and look at a classification map between functional, non-functional, etc., right? So today's session is going to focus on the blue box on the non-functional requirements around performance, scale, and reliability of software products. There are many other aspects, non-functional aspects of software products too, availability, usability, maintainability, security, and many more. Those are things that we won't be discussing at length today. We will be focusing specifically on the aspects of performance, scale, and reliability. But this is just to give you a sense of which branch of software we are focusing. If you recollect the previous session, we had spoken about non-functional requirements leading to architectural considerations, whereas functional requirements leading to design considerations, right? And so we are sort of trying to continue down the same path. And today's conversation will be focused more on the architectural considerations per se. Yeah. So if you remember, we had spoken about design considerations as the detail that is required to achieve a functional requirement, right? So for example, in the context of a bank, a mobile banking application, right? Uh, if I have a requirement that says the account holder should be able to log into the mobile app, use his fingerprint for biometric authentication, and then once authenticated, be able to do any transaction. That's a very specific functional requirement, right? And usually this is the core sort of consideration that you would have when you are dealing with any kind of functional requirement. What is the journey of the customer? How does he or she interact with the system is part of the functional set of requirements. The non-functional aspects are slightly different though, right? So they don't necessarily deal with anything functional. These are the working behavior of the entire system put together. The consumer is only looking at his interaction with the system, but the system behind the scenes may have a lot of complexity, lot of moving parts and components that are interacting to build that interaction between the customer and the system, right? Those essentially are all non-functional aspects, and that lead to the architectural considerations. If we were to maybe put together a level of concept and contrast the 3 points that we are going to cover today, performance, scale, and reliability. Performance, very simply speaking, is a measure of responsiveness or the throughput of a system in a certain time frame. So for example, if you're driving a car, right, and somebody or a bike, for example, right, the performance of that bike or the car is essentially measured in terms of, let's say, responsiveness, in the sense that how much time does it take for you to go from 0 to 60, right? So that is a measure of performance. And usually if there is a bike that can go from 0 to 60 in 4 seconds, versus another bike that can go from 0 to 60 in 7 seconds, you would say that the first bike is more performant, correct? The performance can also measured in other ways. So, for example, if there is a bike that and we can talk about throughput over here. So throughput is essentially a amount of work that is accomplished between a certain time frame, right? So, for example, in the same case, like for example, we were to take a bike and we want to measure its throughput, right? Bike A may have a throughput of, let's say, 40 kilometers per liter, right? And there is another bike B, the same bike B, which we said like was inferior in terms of performance, but in terms of throughput could be better because it's probably got a lower powered engine, but is able to take you longer distances, and therefore the mileage is in some sense a throughput of the system and better for bike P because maybe it goes 70 kilometers per liter vis-a-vis the first bike that only went 50 kilometers a liter. Correct? So performance can be measured in terms of responsiveness or throughput. Uh, Responsiveness is usually measured with in the context of speed, etc. Throughput is measured in terms of efficiency or some kind of a work output that is generated by the system. Scalability is the ability for the system to continue to meet its performance objective as the demand increases. Demand for the function for which the product was built increases or decreases as well, right? So one good example, again, I'll take the same bike example, right? So let's say you take the same bike on a hilly terrain, right? And the ability for that bike, if the bike is able to give you the same 70 kilometers per liter, even on a hilly terrain, then you would call it extremely scalable, correct? If the drop between the mileage on a standalone road and on a slightly inclined surface is not too much, then you would still say the from the performance standpoint that the way the bike was built is a scalable model, right? But if the performance drops, let's say 90% between a travel from here on the main road versus a travel from the main road to Nandi Hills in Bangalore, then there is a significant question mark on the scalability of the system, correct? The last one is reliability, and the reliability of the system is sort of defined as the ability for the system to be able to deal with adversity, right? And in a manner that it is graceful, in the manner that it is durable. So, for example, uh, in terms of just the bike example that we were talking about, right? How reliable is the bike, right? After a service has been done, does the bike uh, uh, not break down after 1,000 kilometers? Is a good measure of reliability, right? So you did a servicing for the bike, and then can I run the bike for the next 1,000 kilometers without a single failure, right? Or without any kind of a fault in the system? I think that is a reasonable indicator of reliability. So, so some of these kinds of things are what the concepts are taken into software as well. And so we took a very simple example of a bike, but you can take this to software and be able to measure the performance scale and reliability of software components as well. So in software, for example, right, we can take this example further. Uh, let's just talk about the performance example of a software. And in this case, for example, we were talking about this bank software earlier, right? So if this bank software can put up a requirement, a non-functional requirement that says any bank transaction. And what is a bank transaction? It could be a transfer, it could be a deposit, it could be a creation of an FD or a recurring deposit, or applying for a loan, etc., etc. Any bank transaction must not take more than 500 milliseconds. So somebody has put in a performance requirement on the system. It's non-functional, right? In the sense that it's not what the consumer asked for. Obviously, the consumer is going to notice it, etc. But the consumer didn't ask for it explicitly. This is the bank itself coming up with a performance requirement for its system to say that no transactions must cross 500 milliseconds. Correct? So that's a very simple example of a performance requirement. Now let's maybe double down and look at the requirement from a scalability angle as well. Right. So one of the key examples could be a system should be able to allow logins and transactions from anywhere between 1 million a minute to 5 million a minute maximum when simultaneously logged in users are accessing the system. So what does that mean? So essentially that I can predict that let's take an example of a bank like an SBI or an HDFC bank, which has a vast number of consumers that operate their systems every day, correct? So one of the scalability requirements for them could be that any given day, right, right, in any sort of given day, at least 1 million users are logged in simultaneously doing transactions on the online SBI system or online HDFC system. And the system should be able to go between that minimum of 1 million to a maximum of 5 million simultaneously logged in users at any given point in time. So that's a measure of scalability. And again, these are all factors that are thought through, researched by the product management team, by the business teams, because they understand what is the kind of volume that is going to come to the system, how many concurrent users are going to be logged in, how many concurrent users are going to make transactions this month. Maybe this is higher during Diwali, right? And when it is a Diwali time frame, there are probably many more people doing many more transactions because they are buying things, selling things, they are sending money to their loved ones, etc., etc. So the activity may actually go up tremendously as well. So at that point in time, there will be new requirements that say that, look, in this month during Diwali in November of 2025, I will need at least 10 million simultaneously logged in users making transactions on the system. So those are scalability requirements, and it may vary from time to time. As time influences some of the workload that is going to happen, the system should be able to scale up or down depending on the nature of activities that are happening in the system, right? So that's an example of a scalability requirement. And then there is this concept of reliability, right? And imagine a situation where across India, there are probably hundreds of thousands of institutions, banks, private organizations, public sector organizations, schools, colleges, etc., who are transferring money on the first day of every month to their employees. Now, the number of employees in India is probably in the hundreds of crores, right? Or maybe late 70, 80 crores. Now, for each one of these people, right, on the first of every month, a salary transaction happens where the salary gets deposited into their accounts, and it has to happen on that day. It can't fail, etc. So there are reliability requirements that start coming in, which say that on the first of every month, when the salaries are being credited, the failure rate of a salary credit transaction should never be more than 1 in 1 million, right? And to be very honest, this is probably 1 in 100 million is what we are talking about as realistic numbers. But as an example, right, you can put up a figure and say it can't be more than 1 in 1 million, right? So this is sort of the way that you look at the performance, scalability, and reliability requirements of the system. And this is a very essential part of non-functional requirements of software design. So what happens if you don't think about the performance, scale, and reliability issues for products? Well, all of us have to agree that it is a very critical aspect, right? The three examples that we just took, it tells you how important some of the requirements for such systems can be, especially if they are very business critical, if they are very mission critical, right? And things don't happen. Imagine like one fine day, let's say we didn't even think about performance, scale, and reliability of the Aadhaar system, and imagine the kind of problems that can happen if the performance, scale, reliability requirements of the Aadhaar system are not very clearly outlined somewhere. So the repercussions of that could be tremendously ubiquitous, right? So people will get stuck at airport. Nowadays, even airports have Aadhaar lines for checking into the airport, right? So imagine the kind of problems that is going to happen where people are not able to enter the airport because everybody used to do Aadhaar authentication to get inside. What happens to many people who are doing Aadhaar authentication for their driving license, for opening a bank account, for operationalizing or doing KYC for their bank accounts, or linking it up to their passport, or like hundreds of other things that happen on a daily basis, where it is probably in the thousands of crores of transactions that are happening every day with an Aadhaar authentication, an Aadhaar OTP, etc., through the course of the day. It is. Is there a question, Jayant? Jayant, is there a question? Jayant, if there is a question, speak up. Otherwise, you can go on mute.
Renewable energy system. Renewable energy system.
Okay, I see that there are a bunch of questions. I'll pause for a second since we already paused. Kanagalakshmi, Jeba, Arokya, Jyoti, do you have any questions that you want me to take? Okay, I will assume that there were no questions and the raised hands were by mistake. So let's go back, right? So customer satisfaction is going to be very, very critical. Business success, right? And if like for example the Aadhaar authentication doesn't work, will any business trust Aadhaar anymore? They will want to do their own way of authenticating, etc. Right? Then the whole value proposition of doing Aadhaar authentication is a question mark. Competitiveness, right? Maybe this is a product that is doing, let's say, an OTT channel, right? And if it doesn't have performance, scalability, reliability requirements in place, and they keep failing, would you, as a consumer of that OTT platform, not want to move to something else? Obviously, you would want to move to something else. And then finally, there is a reputational hazard, right, and a risk that you are incurring by not thinking about performance, scale, reliability. Because when you start doing your business at scale, and your systems are constantly failing again and again, then there is a huge red mark on your reputation. So you don't want your brand image to get tarnished. So that's another very important aspect, an implication if you don't think about performance, scale, and reliability as requirements for your software products. Right. So we will go to the next slide. Is my screen visible? Sorry, I think it got minimized by mistake. Just give me a second. Just give me a second, guys. This. Are there any questions from anyone while I pull up the slides again? Uh, Please let me know if there are any questions. Sorry, I apologize for the mix-up. There was something wrong with the slides. Okay, so let's take an example around products and the reputational challenges, right? I have two news articles, right? And uh, A was for a Hotstar, sorry, for a OTT channel that was airing FIFA World Cup, and for whatever reason they failed miserably. For the first 3 days, the first maybe four matches or five matches of the FIFA World Cup, even though these were the exclusive telecast rights channels, they were not able to share a single minute of video for the first 5 days, right? So, and then on the right side, there is scenario B, where we are talking about a different channel which has probably tried to beam a World Cup semi-final, Cricket World Cup semi-final match with a roughly the same number of users that wanted to get logged in. And so you can see the difference between the two news articles. Which one of the products would you like to be associated with? Option A or option B? And I think if you have if you can start putting in your maybe notes on your uh, chat. So which one of the two products would you opt for if you were sort of dealing with the situation A versus B in the context of performance, scale, and reliability? Anyone? One is good and one is bad, right? So it shouldn't be too difficult to make a decision. Go ahead, Arokia, Jennifer. Go ahead and you can put in a message with your answer. Option A or option B? Okay, no one? All right, we will proceed further in the interest of time. So the answer is obviously option B, right? So because the news is actually positive that they were able to scale to a certain number, and we see this even for the last few IPL matches, for example, we very easily see 40 million, 4 crores, etc., as being the daily number of viewers, which is a very, very good thing. Anyway, so let's now talk about like performance in a little more detail. And we said that performance is the measure of responsiveness or throughput of the system. So there are maybe two very widely used and one very controversially used indicators of performance, right? Latency is obviously a very key term. Latency is again the time. It's a function of speed, right? And so latency is really just the time taken for an operation to happen. So in remember we were talking about the bike scenario and how long does it take for a bike to go from 0 to 60, right? So you can say the latency for going from 0 to 60 is about 4 seconds, and that is a good measure of performance, right? Or throughput, amount of work done in a period of time. We said maybe kilometers per liter, or efficiency of the bike is in some way the throughput of the system that you are able to achieve. The third one is accuracy, and more like success percentage versus failure percentages, etc. But we will leave that aside because commonly you will see these come up in literature as a performance indicator, but really this is more a reliability indicator than a performance indicator. So accuracy, I think, while you will see this in common conversations being associated with performance, really is a measure that is associated with reliability. Okay, so latency, throughput are the two ones to remember. Accuracy used in the context of performance, but actually really belongs to the reliability category. So let's talk about reliability latency to an extent, where we'll take an example, an illustration, and maybe talk about what latency means for this. So I have a very simple example over here. The green person is trying to make a WhatsApp call to the blue person, right? And what do you think will be a measure of latency for this system, for the WhatsApp system? Anyone who wants to take a guess? So, in the context of this software product called WhatsApp, what is the latency when the green person is trying to make a conversation or a call to the blue person? So if it is about sending a message on WhatsApp, what do you think is the measure of latency? Anyone? This is a very quiet class. Nobody uses WhatsApp? Interesting. Okay, so latency in the context of WhatsApp is the time it takes, as an example, is the time it takes for the green person to send a message that goes through the WhatsApp infrastructure and gets delivered to the person blue, right? So it's essentially a time that it takes to say hello from the green guy out here to the blue guy out there, and so the time it takes for it to be the message to be delivered is the latency of that system. So that is something that we need to understand. Uh, Throughput is another concept. So in the same context of WhatsApp, so what is throughput? An example. So let's assume that the green person is at a rock show, right? And they are listening to let's say a band called Agam, and uh, this person tries to make a WhatsApp call to his friends, right? All his friends, his college friends, and he wants to tell them, look, I am at the show, right? So to be able to do this entire activity from a throughput standpoint, what do you think is happening over here? Can somebody define a measure of throughput for this particular interaction on WhatsApp? So I'm giving some examples over here. If you were to send a 1 minute 720 pixel resolution video, right? Uh, it is about 60 MB total in total. If you want to send 1 minute of audio at 8 kilohertz, it's about 4 MB. So you can imagine that if it is a combination of a video, there is a little bit of video, there is a little bit of audio, putting together a 1 minute call, and this is low resolution video. 720p is not high resolution video. So let's just assume that he is using low resolution video and a 8K audio. It's about 64 MB that is being sent across in 1 minute, right? So which means it's about 1 MB per second that has to be transmitted between the green person and his friends, his college friends, all the four blue guys, or all the five blue guys who are probably in different parts of the world, right? So that's the throughput of the system. Each call is probably incurring a megabyte of information per second almost, for it to be relayed to five people, all distinct places in the world. So that's a measure of throughput for this system. So just keep that in mind, that from and now we have taken two examples, right? One is software related, one is non-software. You've been able to understand the notion of latency, which is roughly equated to speed. And then the second one is about how much in terms of work are you getting done, right? And a measure of throughput of the work that is getting done. In the non-software case, we took up like the efficiency or kilometers covered per liter as an example. And here we are taking about 64 MB of data, which is 60 MB of video and about 4 MB of audio getting transferred per minute, to be able to establish a call and be able to stream this much amount of information in 1 minute. So that's roughly the throughput of the system. right? So we said we won't talk about accuracy, but I'm just putting it up here as an example so that there is a little bit of continuity to talk about it. So from an accuracy perspective, when all these calls are happening, right? A person is talking to his group of friends, another person is talking to a friend, etc., etc. The number of times the call drops or the call cannot be initiated is a measure of accuracy, right? So total number of attempts that somebody makes in terms of being able to place a call, right? And in those number of attempts, how many succeeded versus how many failed is the measure of accuracy, or it's actually a reliability concept. But I'm just putting it up here from the perspective of just being able to understand this with the same example, so that there is continuity in terms of how we want to take the example forward. So this is a good example of accuracy as a example that we want to take from a performance standpoint. The next slide I have is about being able to take uh, performance as a measurable quantity, and some of the tools that will help you, some of the ways that you can measure performance, and some of the tools that will help you measure performance in a repeatable way is essentially what we are talking about here. So if we were to take the concept of performance and try and bring it to the hardware world, right? You can look at performance in terms of CPU utilization. You can look at performance in terms of storage utilization and IO rates. You can look at memory utilization as an example for performance. You can probably look at network bandwidth utilization and usage also as an indicator of performance. When it comes to software, you can look at request per second or data transferred per second. You can look at response times or time it takes to serve a request. And then success or error percentages. Again, controversial, but we will just maybe include it in the context of the performance discussion. So to measure all of this, there are tools that are available. Uh, so for example, on the system monitoring standpoint, there is tools available that will allow you to do network dumps, that will allow you to do virtual memory statistics, that will allow you to pick out system statistics, the CPU usage, etc. Sysstack, top, IOStack, VMstack, Nmon, TCP dump. These are all great examples of open source tools that are available out there that anybody should be able to deploy, look at system performance, trend it over a period of time, and make inferences. Right. Similarly, from a software application standpoint, there are tools like JMeter or Apache Bench that will allow you to test any kind of an application, whether it's a web application, whether it is a database, whether it is a TCP-based protocol application, whether it is messaging infrastructures. It doesn't matter, right? You should be able to take one of these tools. They have very pluggable models for very different use cases, and you should be able to measure the performance of the system, request per second, response times, accuracy, failure rates, etc., all within the same tool, very easily through a very simple test, right? That you can record, replay again and again later as well. So JMeter, Apache Bench are again open source tools that you should be able to make use of for software application performance testing. And then finally, there is user interface as well. And so from a user interface perspective, typically these days there is just browser applications involved, right? So there are tools like Firefox DevTools or Selenium WebDriver browser that will allow you to simulate browsers on various different stacks, the ability for you to look at network operations that are happening within the browser and how much each network operation is taking, how much of the data is cached versus how much is actually going to the server and bringing things down, how much data is being exchanged for every request that is made from your browser to the server. All of these statistics are available as part of some of these browser frameworks or browser tools that are available, again, open source and free for use. So now that you have measured all of this, the way to interpret some of the measurements is through visualizations. And there are tools like Graphite, Grafana, or even the Elastic Stack, an ELK or an OpenSearch, that will allow you to feed in this data and then be able to look at performance metrics over a period of time, so that you can trend it, you can analyze it, you can find certain insights around performance of your application, and then be able to do course corrections, right? And be able to do what is called as optimizations, etc. So the combination of measurement tools and visualization tools, and all of them open source, the ones that I have mentioned here are all open source, will allow you to measure and manage performance in the computing world. Right? So usually, when you do this analysis, there are few things that you will notice always. So there is obviously reasons why there are performance problems, and there are typically associated resolutions for each one of those reasons. So usually the findings are that initially when we were doing the architecture or design for that software component, we didn't think through very well, and the focus on performance was not there during the design phase. So how do you correct it? You actually start imbibing performance as a first class requirement as part of the design phase itself. So when you start designing with performance considerations in mind, it leads to a better architecture, it leads to better design, and then you will start seeing lesser and lesser problems when you deploy your software down to the consumer. Right. So the second most common reason is in algorithms or data structures that haven't been used wisely. And I'm assuming many of you go through courses in your college through the first maybe 6 semesters or so that are focused on algorithms and data structures. And this is where this becomes extremely important, because if you're not focusing on data structures and algorithms, you frequently end up having to revise your code and constantly keep changing and refactoring your code, because inherently something that could have been done in a much smarter and cheaper way ends up utilizing a whole lot of infrastructure that is absolutely wasted. Right. So you find that performance problem, it will come up to you in the form of either cost, dissatisfaction from customers to say, hey, this operation takes so much time, I don't know what you're doing, but it looks like a very simple operation and it still takes so much time. So by using better data structures, more efficient code, the right kind of algorithms, you can actually make your application stand out and perform much better than what it was doing earlier, or what you were thinking as the first solution could definitely be improved by thinking about algorithms and data structures. Mr. Tishon, I think you can just please go on mute. Okay. Right. And so the last one is about not having enough performance data to be able to make some determinations about where your problems are. So if you're using the right tools, if you are visualizing it properly, then you absolutely will have a way of being able to measure enough telemetry from your system to be able to make knowledgeable decisions. So these are some of the things that you typically see from a performance problem standpoint, and some ways in which you can end up resolving that. Now I see a question from Jeshwin. What performance metric should we expect when opting for cloud servers over internal servers? So great question, Jeshwin. So when you are using cloud servers, so remember, like in your internal servers, from a network perspective, right, the throughputs that you can expect on a local network is going to be much better than what you see in a cloud infrastructure. So for what that means is that when, let's say, the servers are internally hosted within your college network or your home network, the time it takes for a request to go from one of your local servers to local clients to your local server is a fraction of the time that it is going to take to reach out to a server on the internet. So when you do cloud servers, the challenge is that some of these things are on the internet, and it is not a fast network, right? It is not a dedicated sort of LAN cable that runs between your home network or college network to that cloud server on Amazon or Google Cloud or Azure or Rackspace or wherever you are hosting it. So that is one of the key things to remember from a performance standpoint, that the fact that this is on a public network, and if your consumers are going to access it from your internal network or on the internet, then they are going to see some serious latencies. So you have to design the application now in a way that some of those latencies can be reduced. You may want to look at, like, for example, content delivery networks, caching, etc., as a option to be able to optimize the fact that the interaction between a client that is hosted in your internal college network or your home network is now going to reach out to an Amazon, which is probably 400 kilometers away, 500 kilometers away in Bombay, or wherever, right? That makes a serious difference. So that is something that you would definitely want to have from a consideration perspective. And these are obviously part of a decision-making exercise, trade-off analysis exercise that you do before you opt for a choice between a cloud server and an internal server. All right. Let's go to the quick summary and conclusion, right? So essentially, I think what we can conclude is that performance is a very, very important aspect to consider as part of the design phase. There has to be ways in which you measure and visualize your performance metrics, and you have to figure that out right at the start of the design phase. And then there are obviously going to be some limits on how much performance can be extracted from a system. And so even when you're opting for, let's say, cloud services, etc., you need to start thinking about how you are going to scale up. And we will talk about scale in the next slides. But from a performance perspective, from a single system that you have deployed, there is only this much performance that you can extract. Because at the end of the day, if you look at IO, right? If you look at network, etc., you are limited by the pipe that runs between the network and that host where your server is deployed. So if you want to make it bigger, then you have to either invest a lot of money, right, and vertically scale it up, or there are other ways, and we will talk about that in the next few slides to think about. The next concept is about scalability, and the scalability concept is about a system handling a growing or shrinking amount of work by adding or reducing, respectively, the resource allocation for the system. So if there is a Flipkart big billion day sale on, or Amazon whatever sale on, and during that 24 hours, there is going to be a massive, massive traffic surge that is expected. Then obviously the system has to scale up to that level and be able to handle maybe 500% extra load. And at the same time, 2 days after the $1 billion sale, maybe there is zero traffic on their website, right? And so the system should be able to scale down because everybody is fatigued after the sale and nobody wants to go to Flipkart and buy anything again for the next 3 days, right? So the system should be able to scale down and go to the minimum possible sizing so that the reduction in load from the last few days can then be uh, sort of advantageous from a cost standpoint, running cost perspective, leverage. And so the way you scaled up, the same way you should be able to scale down as well. There is a raised hand. Senthil Kumar, please go ahead. Or uh, Senthamir Selvi, please go ahead. You have a raised hand. Okay, I'll assume this by mistake. So how do you measure scalability? Like we had an easy way of measuring performance, latency, throughput, etc. Is there a measure for scalability? Actually, it's not as straightforward, right? So so it is a concept, and I think more it's not like perfectly measurable, right? But it is easily gaugeable, right? And you can't measure it, but you can gauge the level of scalability that your system has. And what that is essentially how long can you keep increasing the workload before you hit a limit that doesn't allow you to scale further, is the scalability side of the house. So you can either do this going up, you can do it to the bottom also, to say below this I cannot scale down, and beyond this I cannot scale up. So if you have those two numbers handy, that is the measure of scalability of a system. And the only way to be able to get to those numbers is to simulate, test with various different kinds of workloads, etc., with various different sizings of your environments, and hit the point where the system breaks. Either minimum possible to be able to sustain, or maximum possible that you can sustain in the event of a scale up. Right? So those two things will essentially give a scale up function and a scale down function, and a break point where the system starts breaking when you reach the scale down point or the scale up point. Right? So you keep that as a benchmark level, and then you keep sort of adding more and more capabilities and measuring if those benchmark levels can be sustained. So this is the way scalability is typically measured. It's a different. It's not as scientific in terms of measurement quantities that can give you an indicator of scalability, but there are very well established methods that you can make use of to get a good amount of understanding of how scalable your system is. I see a question from Jeshwin Anthony again. Uh, what would be better when considering applications with high traffic rates, in terms of latency and cost efficiency? So let's maybe I have an example towards the later part of the session, Jeshwin. So let's hold this example, and I think I will revisit this question when we do that section. So I hope that's okay. All right. Okay. Right. So let's take an example, right, of scalability strategies. And so two ways to scale is either you can do vertical scaling, which means that if you have a server with two CPUs and 6 GB RAM, you can probably buy another server which is maybe 4 GB RAM, right? Or four CPUs and 12 GB RAM, right? Or you can keep going up and up in trying to scale up. So the same server can essentially be vertically scaled up by adding more horsepower, by adding more memory, and you have a better server that you can scale your workload up to. So great to start with. I think it's a very simple way to think about the problem and implement it. Uh, but remember, like when you do this change from a 2 GB to a 4 GB, sorry, 2 CPU to a 4 CPU machine, there has to be some kind of a downtime or a scheduled maintenance time. So that's a big challenge. Uh, in some cases, it may reduce licensing cost. In some cases, it may be impacting that it takes licensing costs to a higher level as well. Depends on the number of cores, etc. Because some software is licensed by number of cores. But yes, so you can definitely do that, and it is a very simplistic solution. A slightly different way of scaling is by saying that you do what is called as elastic scaling, which means I can scale out or scale in, right? And this is about adding more nodes of virtual machines or machines, or hosts, as they are commonly called, to the system to be able to scale further. So it doesn't involve a downtime, because the moment for example, the example that Jashwin said, that if there is a high traffic rate, what do I do? I mean, my server is not going to be able to handle that load. Then either I do vertical scaling, where I bring that server down, I add more CPUs, more memory, bring it up again, and then the load takes over, or I add one more machine and I do some kind of a load balancing strategy between the two machines. And that's sort of horizontal scaling for you, where I did not have to take a downtime or a scheduled maintenance, but I just added one more server on the fly, and the load balancer is made aware of it, and it sort of load balances the load between both the servers. I can extend it and bring in three servers after a point in time. Maybe 10 servers, maybe hundreds of servers, or in the Flipkart Big Billion Day sale, maybe this is tens of thousands of servers capacity that is getting added for just the duration of that 1 week, right? It is about, I think, if I remember, it's about like 20 or 30,000 servers that are getting added on the fly just before the Big Billion Sale. And those 30,000 servers are brought down right after the Big Billion Day sale. So those kinds of things you can think of if your system is horizontally scalable. Otherwise, you have to put up a maintenance page that says my system is under maintenance for 10 minutes, change your server vertical scaling, etc. Add more CPUs to that machine, add more memory to that machine, bring it up again. A lot of work, right? So even though it is scalable, it is only vertically scalable. It doesn't give me the benefits of horizontal scalability and doing it at my within my control to say I should be able to add capacity any point in time. So that's where the horizontal scale out strategy starts coming in. So one of the conclusions I want us to take this is to say that the goal for any software system is to scale linearly, which means if I, for every 10 users that get added, if I can say that I will add one more machine, then I think I am scaling linearly, right? So the ability for us to come up with a function that says as traffic goes by a certain number, I will multiply it by a certain number of machines, right, as a offset to scale out. That kind of a model is called scaling linearly. It shouldn't be that for the first 10 users you need one machine, the first 20 users you need four machines, for the first 30 users you need eight machines, which means this is not a linear curve. This is going exponentially up, which means after a point you're going to start seeing some serious cost problems. And unless the system scales linearly, I wouldn't really say that it is scalable at all. It is not scalable. So that's something that you need to remember. The ability to add incremental capacity as needed on based on like traffic patterns, etc., is a very good hallmark of how scalable your system is, right? And the key thing is, as you are scaling out, you have to understand that you have to keep costs in check. So one example I can give you is that when we do vertical scaling, right, beyond a certain point, beyond let's say 8 CPUs and 24 GB memory, anything that you opt for will be significantly more expensive because those become very niche machines that you are opting for. And if you have niche machines deployed, they are not commodity hardware, but niche machines that you are deploying to suit some kind of an application of yours, that means that you're not thinking right, you're not designing it properly. Because ideally, this is about breaking down work into small chunks so that even commodity grade hardware can handle it, right? 2 GB, two vCPU or CPU machines, or a quad core machine that is very normal these days should be able to handle that kind of a load. And then when the load increases, you should be able to add one more of those machines, two more of those machines, like 10 more of those machines, as and when the load keeps going up. So if you're able to manage it that way, I think you've got your costs in order, right? So I think, Jashwin, that to some extent sort of addresses a part of the question that you were asking. But I have an illustration later that we will go through that will explain this even better. The third concept that I want to talk about is reliability, and really this is the ability to tolerate faults, right? In a manner that is graceful, in a manner that is durable. And when I say graceful, durable, it means that when I say graceful, it shouldn't show up in a very bad way to the user that when I'm making a transaction, like constantly that transaction keeps failing. The ability for me to be able to take that transaction and say, well, there is maybe a little bit of delay in the system and I will be able to handle it in a few minutes, etc. It's a graceful way of handling the situation, the adverse situation at hand. But it is durable enough to say, since I handled it gracefully, I took your transaction. Maybe there is a little bit of a delay, but it will get done. And I will make sure that it gets done. I can give you durable guarantees that it will get done, is basically what the reliability of the system is. So that's a short understanding of what reliability is. When we talk about reliability, I think we've got to make sure that we understand that this is about reliability is about giving or producing results consistently and accurately over a long period of time. Uh, it may deal with hardware errors, software errors, user errors, etc. Many different kinds of erroneous situations, and still be able to in a resilient way handle that fault, right? And do it in a manner that when you recover from that problem, right, you've not lost anything. And so that is the durability guarantee that the system needs to provide, right? And so one of the fallouts of reliability, right? And remember, when we started the conversation, we said there is a non-functional aspect of availability associated with system requirements. And I think reliability is one of the biggest contributors to availability. If your system is not reliable, it generally is not available as well, right? So and vice versa too. So remember that the root cause is reliability. It results in availability challenges and compromises that need to be made. So the more reliable your system is, likely that it is more available. So that's something that I want you to take away from this exercise. Now, we were talking about measures of performance and scale, etc. Right? Now, I want us to maybe uh, uh, look at something similar from the concept of reliability perspective, right? So, reliability actually is a very interesting concept, and a lot of the concepts around reliability come from a very special branch of engineering called systems engineering. And I don't know if many of you have taken systems engineering courses. Has anybody done control systems in this group? Anyone who has gone through a course on control systems or even reliability theory, uh, let me know if you have. No? Okay, no problem. So many of the concepts for software reliability also comes from are borrowed from systems engineering perspective, and reliability is a very key concept there. Uh, so in software specifically, right? Uh, the repercussions of the reliability aspect is quite large. It will span availability, it spans maintainability, testability, many other aspects of non-functional side of software design. Uh, the simplest way that it can be measured is in right? What is the success rate of the system? Or inversely, some people like to look at failure rates as well. Both are interchangeable because one is the complement of the other. So success rate, if you are measuring success rate, failure rate is one minus the success rate, right? So you can look at the number of events that have happened in the system. You can take the number of successes out of it and then be able to look at the ratio, and that gives you the success rate of the system or a measure of the reliability of the system. Now, the complementary rate, like I said, is what is called as failure rate. And many a times in modern reliability engineering work around software, and there is a completely new name to it called SRE, right? So it is software reliability engineer or system reliability engineering. That kind of a function commonly looks at failure rates as an indicator of the reliability measure. So the higher the failure rates, the lesser the reliability of the system. And many a times these statistics are used to make informed decisions about how to act on a fault that is happening in a system. So there are probably some kind of thresholds that are defined to say if you have an error rate of or failure rate of 0.0001%, then just an alert is going to be raised and people are made aware that something is wrong in the system. But if it goes to 0.0002, then a alert is going to raise and somebody has to get into the system and try and resolve it using a standard operating procedure. So these are very common systems engineering concepts that are now applied at scale on software. And the whole function of SRE, systems reliability engineering, is essentially baked in the kind of concepts that are borrowed from systems reliability theory and systems reliability engineering. So in software too, we are starting to use that more and more. And the term that the SRE professionals or systems reliability engineering professionals will use is called a SLI, or a service level indicator, that every one of the SRE personnel is tracking and making sure the system is living up to the standards for systems level indicators that have been defined. If it crosses or breaches that threshold, then there is an immediate response that needs to be planned out. There may be additional capacity that needs to get added. There may be some optimizations that need to be added. There may be some intervention that needs to happen in the system by throttling, etc., etc. But these are all part of a run book that the SRE professional will have, and he's just going to look at those numbers and make decisions to figure out what is the right next step to do, right? And apart from the SLIs that we spoke about, these SRE professionals are looking at key performance indexes for themselves, right? And so these are what is the mean time between a repairable failure, right? And this mean time should ideally be very, very high so that there is no failures in a large duration of time. So you are trying to essentially maximize the MTBF, or mean times between failures. Mean time to resolution should be as low as possible, which means after a SLI has been breached, or a number that has been hit, to say the failure rate went from 0 to 0.0002, and that has triggered an alert, I should be able to resolve that alert so that the system comes back to 0.0001 at the very least, which is an SLI that I'm happy with. Then I need to reduce the time it takes for me to bring down the reliability or the failure rate from 0.002 to 0.001 within a matter of a few seconds, or a few, or at most a minute. I will set targets for myself like that, and I will. This is the performance of the team that is now being tracked to say if there is a problem, you should be able to resolve it within the mean time to resolution that is dictated by the organization. Right? Mean time to failure should also be very high, as much high as possible. So MTTF is another metric that is tracked very, very closely. And this, the goal is to keep this as high as possible within the system, because essentially you're maximizing the success times, and the system is not failing for a long duration. This is also indirectly a reflection of the reliability of a system in the long term. So MTTF and MTBF have to be as high as possible, and MTTR has to be as low as possible for the system to be extremely reliable. Okay, so this is a concept that is very widely used across the world. This is not just a software concept, although nowadays it is being used very heavily in the software industry as well. This is something that manufacturing industries and any place where systems are being developed, automation systems or supply chain systems or any kind of supply chain management also thrives on these kinds of quantities. But these are concepts that are borrowed from reliability engineering and are applicable to a variety of different industries and domains. So you've got to keep these concepts very clearly defined in your head. And this is not exclusive to software. This is what I would tell you. Right. So this table sort of calls out the kind of faults that you expect to see within a software component, right? So there could be hardware or infrastructure faults. Like some of the common ones is disk failures, right, or storage failures. So you have a mounted storage, and that storage, I mean, it's at the end of the day hardware. It is a either a disk, a spinning disk, or a SSD device. They all fail, right? And at some point they have a lifespan, and if you exhaust that lifespan or it is used more, etc., they are bound to fail. And so the resiliency characteristics for this is how redundant are these disks. So if there is a failure, can I quietly switch over to another disk without the remember the numbers that we spoke about, MTTR, MTBF, right? MTTF, all of these being in a manner that are within the numbers that my organization dictates. And if they are, I essentially have a great way that I can deal with a hardware failure like a disk that is failing. Similarly, from CPU perspective, right? So high CPU usage, right? Constant high CPU usage, or a machine sort of that is heating up more often and shutting down. These are all classic indicators that something is wrong, and either you have to do some capacity enhancement, or you want to be able to file a ticket on your development team that has to go back and optimize certain piece of code, etc. Obviously, after looking at like some of the benchmarking that has been done from a performance indicator standpoint or from a visualization standpoint, identifying what is the problem and how we can resolve it, you either decide you want to auto scale and add more capacity, or you figure out that adding more capacity is actually going to cause cost problems, efficiency problems, and I should actually go and optimize the issue rather than adding more capacity. Or a hybrid approach where I'll say I'll add capacity for the next 3 days while the optimization fix comes in. For the next 3 days, we will add more capacity and tide over the problem. But on the fourth day, I expect that the optimization will come in and I will decommission the additional capacity. So these are all strategies that reliability engineers make use of. The last one is from a systems perspective, network outages, and that happens quite often too. An Airtel that is supplying the internet bandwidth to my college infrastructure or to a cloud infrastructure may go down, and the cloud infrastructure may have backups, etc. But sometimes you can't do much because the network outage is because of a broken C link somewhere, right? Which is basically the entire sort of backbone of the internet for countries, right? Somewhere in the Atlantic, if there is a breach and the cable is broken, then obviously, like, we are going to have serious network challenges. So how do you deal with situations like that? What kind of redundancies have we built in? What do we do in case of those outages? Can I shift from one region to another to be able to maintain business continuity? All of these are aspects that a reliability engineer has to think about, an architect has to think about before they commission an architecture. Similarly, there are challenges on the software side as well. There can be bugs, there can be application performance related challenges, there is unauthorized access, etc. That sort of keeps coming in. And for reliable software, right, there has to be an ability for us to be able to manage these things well. So for bugs, for example, by writing better unit test cases and making sure code coverages are very high, by doing thorough code reviews, right? The ability for us to be able to gauge that some code is going to get into production and break things is extremely important. Uh, from an optimization perspective, right, the ability for us to look at 95th percentile numbers or 99 percentile numbers throughout the day and make very good inferences about performance insights is extremely important, because you're constantly going to be dealing with requirements about either adding capacity, removing capacity, making optimizations, etc. And so you want to be on the top of things and know where the root cause is. Is it going to take me 1 week to fix? Is it going to take me 1 year to fix? And then be able to make decisions on how you want to deal with the problem. So this is very, very important, again, to have metrics and being able to monitor the metrics of a system at a very granular level through visualizations, etc., so that you have good insights and you can operationalize those insights into how you run your software, right? And how you prioritize certain fixes, etc., activities, etc., in your roadmap. That way, your cost functions keep going down. The last one is user errors, right? And so these are things beyond the software's control. Big billion sale, for example, there is sudden surge or there is a sudden sale campaign, and you see a lot of requests coming into the system. A user does something really bad to the system and it has compromised the system, or some kind of deployment configuration errors, etc., that can happen. So many of these things, again, right, through putting in adequate safeguards or governance, putting in some way of architectural considerations which lets you isolate load that is getting into the system, so that not everybody in the system is impacted, only a certain few potentially are impacted by the problem. So these are all considerations from an isolation standpoint that you think about. You could do rate limiting, for example, to say no one user gets an unfair amount of time on the system. And so you can implement fairness schemes, etc., or implement unfairness schemes where you're sort of looking at whoever is using the system unfairly and basically throttling them down are very commonly used methodologies to deal with such surges, etc. Right? So across many different kinds of faults and types of faults, there are very established methods available so that you can think about them and improve the resiliency of your applications that you build. And again, these are not something that is very software specific. These are obviously applicable to a variety of different industries from a business continuity standpoint, etc., are extremely critical to maintain the reliability of the system, right? So I think in summary, right, you must manage the reliability of a system by having very good performance indicators that is implemented. So these indicators, right, in some sense, are going to give you the right kind of visibility and inferences from your system to be able to prioritize activities, the ability to automate uh, actions that needs to happen to scale up or down, and therefore improve the reliability of the system. We also spoke about some of those three measures, right? Mean time between failures, mean time to failure, and the mean time to recovery as three very critical reliability metrics that every SRE team or systems reliability team, engineering team has to follow. And by doing that, then you can sort of achieve customer satisfaction, better reliability from the system, and better sort of understanding of how to scale the system up and down. So I'll pause here for some questions, and then we probably have some interactive sessions to take on next. So any questions from someone? I know, Jashwin, I have to get to your question, but any other questions that come from you or anybody else in the audience? Happy to take them right now. Okay. Maybe we will let you think through and come back with a question. So in the interest of time, I'll move forward with the example that I had, right? And I'm going to take a very real world example. This is not software related at all, but it will sort of help us with understanding the notion of performance and scale and reliability to a certain extent. Uh, so now let's maybe take an example, right? You go to a bank, right, and you are standing in the line. There is only one counter in which there is a teller, and you've gone there to withdraw some money from your bank account, and the queue just is increasing, is just growing, and this person is not able to move fast enough. How many of you have been in a situation like that and felt really bad and something better should be done? Anyone? And if you think a bank is a bad example, somewhere else you have had to stand in a queue and bear the brunt of a single queue where you got stuck when you were in a hurry. Happy to take that example as well. A bank is just a hypothetical context that we are putting ourselves in. Any other such similar situations for anybody? Train ticket counter, wonderful, Jashwant. So very similar, yes. So you end up being in a situation where you're physically standing in line, and this person, there is almost a sense that like this person is inefficient, right? So usually frustration creeps in into our heads. We think that the person who is at the counter is very inefficient. He's not productive, and so like the first thing that crops into our mind is change this guy, right? Or change the person who's at the counter, put in somebody who's more experienced, who has handled this a little better. This guy looks like he doesn't know what he's doing, or she doesn't know what she's doing. So we have all been in this situation. Everybody understands this situation well, right? Because we are going to take this example and try and draw parallels on like from a systems perspective with performance, scale, somewhere from a reliability perspective. Right. And how many times have we gotten into a situation where such a queue is going on, and then somebody who's being served starts arguing or complaining that the ticket that was issued or the money that has been given to them is incorrect, right? Some name is mismatched, or my KYC is not proper, or I asked for 10,000 rupees and you've given me 9,900. Often that happens, right? And so these are common things that you will see in a queue, and the frustration just keeps building up. Am I right? So this has happened with everyone. Yeah. Okay. So now let's maybe look at all of this and see what is going on. Right? Multiple things are at play when you look at this queue. So 5 minutes per transaction at the very minimum, not acceptable number, right? From a uh, okay, so there is a question here. I'll just look at it. How should one forecast incoming traffic in near future and set up computational parameters? Yeah, so great question, and we will talk about it. Yes, it's a good question. So we will talk about this even in the context of this example, Jeshwin. So let's take this example and now look at what all is going on in this system, right? So obviously there is a teller's inefficiency, so which means that maybe this person was new to the bank or new to the IRCTC system, and they're just getting used to it. This is their first day at work, and obviously they will be slow, right? Because they don't have the experience of doing this many times through many years, etc., and their speed is going to be a little lesser than somebody who has been there in the system for ages. So there is definitely this portion of the teller's efficiency. There is the amount of work that needs to be done by the teller to service that one client. So maybe to be able to get this ticket, right? This person is constantly asking them. He's asking them, "Oh, do you have first AC? Do you have second AC? How many seats do you have in third AC?" There is a series of questions that is being asked, right? And this is not just one work to issue some money to me, but I also have to do my KYC. I also want to get my address updated. I also want to make sure that I'm adding my child's name in the family account, etc., etc. So the unit of work that that person is doing is actually 3 units of work. So we think it is one person in the queue, but that one person depicts 4 different jobs that possibly that work involved the teller doing, right? And so there is more work in the system than we think that there is. So that could be one of the problems, which means the workload on the teller is higher in terms of the usual things that we expect the system to be doing versus what we are seeing in reality as the queue pans out. Uh, Customers' expectation versus the reality. So sometimes I expect that my ticket should be delivered to me in 20 seconds, but the whole series of steps that is involved, checking availability, making sure that the destination and the source and the destination are matching up, making sure the fare is collected, the fare is deposited, and the ticket print has been given to the customer. All of this cannot be done in 20 seconds, right? And so I think I expect that something needs to happen in 20 seconds, but in reality, there is amount of work that needs to be done that takes at least a minute. So that could be a expected quality of service problem versus real quality of service problem. And then it just could be one of those big billion day sales day, right? And so suddenly there is a problem with the bank, and everybody is getting into the bank to withdraw money for whatever reason. It could be the first of the month, where everybody's salaries or pensions have been credited, and I want to be able to withdraw that money. Now, this takes us to a level where we have to now start thinking critically about the problem. We have to be curious and inquisitive about the kind of challenges that there are in the system. So don't just jump to the first conclusion that you draw that the teller is inefficient. It could be many things at play, correct? And so unless we have the monitoring metrics for every one of these problems, we can't really solve the problem properly. And a classic example is Jeshwin's question on the in-call messages that says that, okay, for instance, for big billion days, how would they forecast the approximate traffic that they would face and set up the servers accordingly? So great example. So since it's a forecast, they probably have last year's data that is available to them to say how many people bought from them between a certain time interval on the big billion day, first day, second day, third day, fourth day, fifth day, so on and so forth. So they have a lot of rich data that they can potentially use to make forecast assumptions. They could probably have a buyer pattern that they have been able to figure out from the data that they have. In this case, for example, I should, as the bank manager, should be able to expect that I have, let's say, 40 senior citizens in my branch, and I am sure that at least 80% of those senior citizens who have no other way of going to an ATM or who are not savvy with using an ATM will come to the bank counter and take that money from the bank teller. So it shouldn't be a surprise to me that on the first of every month there is a queue. Correct? So again, this is data analysis from some metrics that I have looked at from the pattern of usage, and I should be able to forecast what is the incoming load on this day. And maybe on that day, I do something different, correct? And so that leads us to some of the answers that we will talk about now. So now that I have a way to either figure out that this is an anomaly or a sudden surge in traffic patterns that I didn't anticipate, or it is a planned event of sorts where I could decide upfront that I may need more capacity, I may need a better teller at the counter, more experienced or efficient teller at the counter who will probably reduce the transaction time from 5 minutes to 2 minutes and still get the work done. These are all the bits of data that I, as the developer of the software, or the bank manager, or these IRCTC counter manager in the IRCTC booking counter at the railway station needs to have in my hand to be able to make the right decisions. Correct? So obviously there are multiple options to consider. There are trade-offs, and there are many suggestions for improvement. So we can think about it. The first thing that comes to your mind is to basically say replace the person with somebody who's more efficient. Correct? So get rid of that person who's come here today. Replace him by that person who has sat in that counter for the last 10 years, and he is much faster at it. So great. So I can get a better person, or a person who's more efficient sitting at the counter, and he will be able to deal with this better. This kind of a scaling strategy is called vertical scaling. So this is essentially the host who is serving the requests is being vertically scaled from his current throughput of maybe one transaction in 5 minutes to one transaction in 2 minutes, right? So that's a great throughput scaling up, right? Or in terms of latencies, this is reducing the latency in the system by 5 minutes per operation to 1 minute per operation, right? And I can do that by adding a more efficient teller, which means in the context of software systems, this could be that I dropped my one CPU machine and I replaced it by a four CPU machine. That's why the size of this person is a little bigger, for example. So I have vertically scaled the problem area by adding more capacity or adding more efficiency, and then therefore the solution works, right? So you are adding efficient tellers in the bank or the IRCTC counter or the server that is processing all these lined up requests, and therefore I get better scale. So this is definitely one option that we can consider. But is it the best option is always the question. So what are the problems in finding a person, like an efficient person for every counter of IRCTC, or a efficient person for every bank teller in every branch of the bank in India? Very, very hard problem, because you have to train that person. The person has to be trained for many years before he achieves that kind of efficiency. And by the time he achieves that kind of efficiency, he or she wants to do something else, and they want to do a better job. They don't want to sit at the counter at all. So it's a very, very hard problem. And so if you throw money at it, these counter tellers will start asking for more money. In the context of software, as you go beyond a certain level, right? I want maybe a 12 CPU machine with 96 GB RAM. Those machines are going to be very hard to come by. And the more your system depends on such kind of solutions, the more expensive it becomes to run, right? So you have to find a better, cheaper way of scaling this problem, and that takes us to option two. And the option two is for the ability. I mean, to me, the ability to add two more counters, right, in the bank branch, and scale it out instead of scaling it up. So this is called a scale out strategy. And so what happens is when a person enters the queue, they are directed to one of three different counters. And so there is a concept in that direction. So you would obviously see a person at the security gate in bank branches, or at the I mean, there is a counter where a token number is issued, and based on the token number, you are randomly distributed to one of these counters, right? So that's a great example of a way that I have scaled this out. And you know what that token counter is? The place that gives you the token to go and reach out to the counter is actually a load balancer. So in the context of architecture, the ability for me to route me to one of the counters is a classic architectural pattern called load balancing. And this particular box that you see over here is acting as a load balancer, which basically says, hey, I can see this counter free. The next person goes to that counter, right? The load balancer does exactly this. So it looks at who's the busiest, and will route the request to that line, or it will do a random allocation to say, I will take the next person who comes in and randomly allocate to one of three, and which is also a reasonably fair round robin kind of strategy that people use. So busiest server last, round robin, least loaded, etc., etc. These are all concepts that the load balancer uses to route the requests to the right counters. So this is a classic example in which you could have thought about adding an additional counter and adding a load balancer in front of it, and being able to serve the queues a little better, because now you are basically halving the problem that you have had in your hand. So any counter is probably just dealing with three requests, and therefore things will get done faster. So this, in the long term, is a slightly better approach, because it is cheaper to train, cheaper to provision hardware, etc. All the concepts add up in terms of a scale out solution. Now, imagine this at even bigger scale, and this is where the architectural considerations start becoming interesting. So imagine that there was a system where the incoming individual is directed to a specific branch. Even before he goes to the counter, he's first directed to a branch, and then within a counter within that branch. So now this is two levels of routing that are put in place, because now you're going to two different zones, right, or regions, as somebody may say, where there is a global traffic management engine. Is also a kind of load balancer that is routing you and saying, hey, go to that branch that is maybe 100 feet away from here. If you go to that branch, you may get better served, right, and you may get faster served. And there is another branch maybe 100 feet from this road. If you go there, your job will get done in 30 seconds. Now you have to wait here for 10 minutes. So if you have implemented a strategy like this becomes very, very easy to do horizontal scale out. And this is a very advanced way of scaling out solutions. And I want you to remember that this is essentially the concept of how scalability is implemented in cloud solutions. Okay, and you will hear about concepts around availability zones or regions in the context of an AWS or GCP or Azure. This is exactly what that is, that you're going to see load. You better divide your load into various different regions or branches, and then be able to serve them that way. Okay, so scalability and performance improvement and reliability all can be achieved with doing some kind of management, architecture management like this. So I wanted to put this in perspective, and I think, Jashwin, from your perspective, both the questions that you answered, right? What are the different options to consider when you are handling higher traffic rates? You obviously need to understand how to do that, and this gives you a framework. Now, you also remember that, like, within each of these branch boxes, there is only limited square feet available to add the fourth counter, right? Maybe in branch 2 you can add a fourth counter, but in branch 1 you can't. And so you have to keep doing this management exercise, because there are capacity constraints, there are cost constraints, etc., from very different branches, right? So one branch may have a different kind of constraint than another branch. So you always keep all of these considerations in mind before you make a decision about how you want to do your scale out architecture. Okay, so I just wanted to put this in perspective, that these are all very similar problems, right? This problem can be translated into a traffic problem at a traffic signal as well, on how, or at the highway, right? How do you manage toll booths is also a very similar concept, where you can use some of these techniques to figure out how people should be diverted to lanes and therefore to different toll booths, and so that the time that somebody spends at the toll booth is the minimum, and the time that they are doing in transit is the maximum. So some of these things are patterns that can be utilized in a variety of different contexts. There is another example that I wanted to tell you from the perspective of costs, right? And vertical scaling versus horizontal scaling, right? And why, generally speaking, horizontal scaling is while it is complex to implement, is a preferred strategy, because if you keep scaling vertically, and this is essentially a illustration that depicts Moore's law, and what you will see here is that over a period of time, right, there was an exponential growth in terms of how CPUs used to evolve every year. But if you look at the recent past and somewhere in this region, what you will see is that there is a tapering happening. And what this tapering means is that in the next few years, we can't expect CPU capacities to grow up exponentially every year the way it used to grow over the last maybe 3 or 4 decades. That's not how things are going to stay going forward. At some point, right, any small innovation in a CPU because of material science constraints, because of many different aspects, right? We have gone to the limits of what we can do with CPU architecture, the traditional computing CPU architecture. That you're starting to see this taper off, and the innovations are not happening at the same scale that they were happening earlier uh, for the past few decades. So what this means is that CPU performance over the next few decades will taper off, and every small increment will come for a large price pump. And so you're not going to be able to if you have a solution that scales vertically, you're not going to be able to get to a point where you can scale vertically for a long duration of time. That's not going to happen. And you have to look at an option that is much cheaper, because every small increment that we make to vertically scale the CPU, we are probably going to spend 2 times or 4 times the cost going forward from the levels that we are today. So that takes us into the realms of horizontal scaling as the preferred strategy for many organizations now, because those kinds of CPUs are virtually commodity CPUs and can be bought for very cheap prices compared to higher grade CPUs that are really starting to get very expensive these days. So just wanted to share that. And I think uh, this is another example of taking the same Moore's law and translating it into a computational performance problem, right? So why worry about performance when next year there is going to be a CPU that is going to be faster, right? Or I will find a teller who can serve the bank request much faster next year. That's not how things work, because you can't just keep upgrading forever and tend to achieve the efficiency numbers that we are looking for, or throughput numbers that we are looking for. It is sadly is not always possible. There are limits to everything, and we are close to reaching the limits of what the current traditional computing capabilities are. Right. So this is an illustration of how that tapering is happening. It should have gone straight up, but it is actually tapering down now. So with that, I think I'm sort of reaching the end of our conversation. I wanted to have like maybe two or three very fast quiz questions. I want you to guess what these two chips are. These are obviously chips, but can one of you guess what these chips are? The first one looks like a very old one. The green one looks like something more modern, right? See the connections between the chips, the various sort of. Any guesses? No? Okay, let me give the answer. The first chip was actually a guidance computer chip, right? That was used in the Apollo mission. We are talking 1969, 1970, right? At this point. So that yellow color chip is actually from that environment. So look at the chipset, right? It was a 1 megahertz chipset, had 4 KB of RAM, and had 72 KB of storage, right? Compare it with the green chip. Do you know where this green chip fits in? It fits into your charger, because your charger is also a computing device, by the way. And this computing device is essentially doing some computations to figure out how much charge to send to your phone, right? So even before the current gets to your phone, it is going through a computer and getting modulated. That is where the current green chip is being used in a Google Pixel charger. And what I will tell you is if you look at the specs of the charger chip, it is 10 times the size of what guided us to the moon, right? I'm not belittling anything or trying to make some profound statements over here. I'm just telling you that the you can achieve a lot more with less. And yes, the situations may demand us having to do something very expensive, but if you look at what was achievable with a 1 megahertz processor with 4 KB of RAM and 72 KB of storage, it is mind boggling that we can take a space rocket from Earth all the way to moon, land it, and bring the astronauts back with that same guidance computer, right, with such a specification, whereas that specification or 10 times better specifications are being used today to power the charging equipment for our phones. So I just want you to take away that thought that you have to stretch your thought process on trying to get more done from less if you want to be truly good at performance and scale and reliability, because the lesser components you have in the system, the more you are able to get done with less will determine the standards of performance, scale, and reliability for your systems going in future. So just remember that, and I just wanted to give you that. There is another very key thing that I wanted to call out as part of this session, right? And something that is not talked about very commonly in the software industry, but the energy requirements for a data center are probably in the tune of very high consumptions in the world today. So if you look at energy consumptions for a data center, we would probably break this down into three parts: enterprise workloads or consumer workloads, everything that I mean, for a simple Google Maps search for getting to the railway station to the college, right, needs some computing power, right? And this is many people across the world trying to do this computation to do day-to-day things in their lives today. So there is a tremendous amount of workload that is dedicated to doing enterprise tasks and consumer tasks that everyday work needs to happen from. There is a whole lot of people who are doing crypto mining, right? And then there is data transmission, right? Every time we stream a video to YouTube, there is some kind of energy utilization that happens, right? So I want you to think about this. If you put all of this together, what is the energy requirement from all the world's data centers put in, right? And it is a very thought-provoking question because it has very key aspects embedded in performance, scale, reliability side of things. So what is the energy requirements for all the world's data centers put together, right? And I know it is almost unfathomable to figure out what this number may be, but I want you to see this illustration now and make your own judgment calls, right? So data centers, right? And I'm excluding crypto here, right? We will not even talk about crypto because the moment we start talking about crypto, there is a completely different side of compute that starts coming in. It is significantly higher. But even without crypto, if you look at this bucket, right, of 220 to 320 terawatt hour, you will actually see that this data center utilization of all data centers put together that the world has today is roughly equivalent to the top 10 countries in terms of how much the entire country uses from a energy consumption standpoint. So if data center was a country by itself, it would be at the 10th level. If you put crypto mining as well to that list, you get to being the fifth country, like in terms of the most energy usage numbers, right? The ranking would be at par with top five countries, and like you're almost at Russia level. So imagine the amount of energy that goes into computing, and every time we over allocate, we over budget, and put in more capacity than is needed, or use the wrong algorithms, or use the wrong data structures, or don't think about design upfront, we are contributing to significant wastage in terms of what energy consumption means to the entire world. And this is going on, happening for like many decades now. It's just that we don't think about it. If this was airline industry or the vehicle automobile industry, we would have sort of talked about it and cursed those industries to the fullest, right, from a critical thinking perspective. But to be very honest, the industry that I am in, and shame on me, that we don't think about this as a wastage. And the more we tend to not think about very good design, very good architecture, we leave performance problems aside and spend money spinning up compute to handle those performance problems. The gap is going to get lower and lower, and it won't be too many days till the computing side of the world becomes the top consumer of energy. So just keep that in mind, because everything that you do has a social obligation as well. And so for anybody who thinks they are socially inclined, remember that even that one line of code that you write in some way is influencing the utilization of energy across the entire world. So with that, I think I come to the end of this session. I don't have anything more. I can take more questions now. We have approximately 5 minutes to take questions. I'll open it up to everyone to start asking. So these slides will be made available to you if you want to refer to them later. Any questions from anyone? Jashwin, did I answer your questions? Okay. Okay. If there are no further questions, then I think I will give you 3 minutes back in your day. Thank you for attending. If there is any feedback, please share. We will strive to take your feedback and try and make the content a little better. So if you thought that there were certain aspects that you would have liked seeing covered as part of the session, or concepts that we need to go deeper into, then please drop the line through Satkam or your professors. And if that comes to us through feedback, it will be good, because then we can modulate the sessions appropriately. So I hope the content was useful to each one of you, and in some ways has stirred up some thinking in terms of how you would bring in performance, scale, reliability concepts into your day-to-day work. All right. Thanks, everyone. I will stop the session. Thank you.